in these sessions we will go through about brief information about the three-phase separators and the calculation part of the separators. Okay, about the three-phase horizontal separator, we can say that we have mainly two, let's say just two types of the surface separator. The first one is the internal, with which just we have the in which we have the internal baffle, and in this type, in case of the internal baffle, we have the mainly I just wrote written here the I have written here the some submerged baffle, but they are referring to the wires. Uh, let's say just for three-phase separators, we can have two types. Uh, in the first one, we have the wire. In the latter, we have the only boot. Now, just we are going through. We okay. In case when we have the wires, we have the two types. This wire can be submerged wire or submerged baffle. Second type is the wire baffle, which we will okay. Which in this picture, if you see my cursor, okay, that's my say that's our surface separator. That's our inlet gas feed inlet. That's the liquid outlet and the heavy liquid outlet and the light liquid outlet. Here we have the wire. And then we have some internals here which we have not, let's say, just illustrated here because it's a simplified drawing of the surface separator. Okay, here with submerged baffle and with wear baffle, it means that in case of the submerged baffle, normally because here after the wear we are collecting only oil, let's say just the oil liquid. That's why our oil is normal liquid level of the oil in this section is always higher than the wear, is always higher than the height of the wire. But in case of the wire baffle, uh, let's say just always we are overcoming this wire in order to separate the oil liquid from the, let's say, heavy liquid. In the second part, we are using the separation boot. It's preferred for really low heavy liquid flow rates. And here, as you see, just it's a two-phase, again it's three-phase separator. We have the feed inlet here. That's the light liquid outlet, and that's our boot. Just because since we have the very low trace of heavy liquid, that's why we are using the boot here. Also, this application, for example, I have seen. In case of the two-phase separators, let's say just let's ignore this outlet, light liquid outlet. This configuration is also used knockout drum of the flares because we know that normally the gas, just the stream going to the flare, does not contain, let's say just so many. Let's say so much water. That's why we are using boot here in order to collect the condensed water or mainly water because we are just assuming that we have the water in case of the flaring or overpressure let's say just overpressure cases. And but if we have also we can also have other types of liquid. Okay, that's the separation boot. Now let's go to the hold up. Let's say just which are the hold up volumes of let's say phase separators with internal baffle or with wire. Okay, that's our let's say illustration. As we have said, that's a submerged baffle. Here, the color, let's say, the blue or just light blue or zur, here resembling the oil phase. We see that that's the interface between the liquid level. Let's call it water and liquid. That's the interface between water and the oil. That's for always our liquid level is higher than the our oil level is always higher than the height of the wear. That's why and we know that by considering the let's say the Bernoulli equation and the fundamentals of the fluid dynamics, we know that we should have normally the same height here. Actually, we have some fluctuations, but in ideal cases, we have the same height here, same level. Okay, always we are transferring our oil from this side to the section after wear. But in case of the wear baffle, we are always overcoming our wear. That's why we have the normal liquid level for the oil flow rate lower than the height of the wear. But here, the normal liquid level of the oil, even after the wear, is higher than the wear of height of wear. Okay. And for the actually for the in case of the boot, in case for the surface separators, in case of the boot, we are just simply having these hold up volumes. Uh, let's say is that these, let's again define this blue as oil, as our oil, and here we are collecting our water. Let's say the water liquid, and that's line resembling the interface, exactly this one, yeah, resembling the interface between water water phase and the oil phase. Okay, and the next step is about the surface separator horizontal or surface horizontal separators level settings. Here, as we say that the uh, uh, here for the feed inlet we are using reversed pipe, but that's not just a common, or that's not the only rule. We can use several types as we have mentioned in the previous session. Okay, here in case of the two-phase separators, we have only the high level, normal, liquid level, low level, low level, because for the two-phase separators as a liquid we have only one phase. It's as a liquid phase. Inside the separator we have uh, either not either, let's say it's the both gas phase and liquid phase. But in case of surface separators, we are defining in this way that that's our feed section. We have the gas phase, we have the light liquid phase, and then we have the heavy liquid phase. That's why we should define and we should control the levels of uh, the levels of the each phases, each liquid phases. Okay, here we see that we have here high level, high level, high level, normal level, liquid level, and a low level. And here we see that the HHLIL, and here I is resembling the interface. It means just that we don't have the, let's say just actually we are not controlling mainly the water level or heavy liquid level. We are controlling the interface between the high level and the low level. Sorry, between the liquid oil phase and the water phase. Sorry. Here again we have the high liquid interface level and high HIL resembling the high liquid interface level, and the next one normal liquid interface level, low liquid interface, and the low liquid interface level, and the low interface liquid level. Okay, one interesting point regarding this picture, just I want to make a question to you, that could you say me that the please, because here we see that that's the we are using where here, as we see we are using the where here, we are not using wood. But as we as we have just said, for the wear type, we have two type of wears: submerged wear and let's say overcome wear. Let's say a wear baffle when we say wear, overcome wear. Could you please tell me that which, let's say which type of wear we are using in this picture, in submerged or or overcome wear? Yeah, one of you.
It's submerged.
First of all, first your name, please.
It's Patty. Happy.
Okay, Perry. Just could you please repeat your answer?
It's submerged.
Why you are just? Could you please prove it? Justify it.
Um,
Let's say.
because like the light, the oil comes from the upper side. Like the baffle is connected to the, say, there is like its interface between the light between the oil and water, so oil comes from the upper side of the weir to the right side.
But
It's
also, let's say just actually, your answer is correct. Your answer. Thanks for your answer. Yeah. Just you are saying that the oil coming overcoming from the, let's say, just, wear of the separator, but that's also the case for the wear, let's say, the overcome wear or submerged wear. But the difference is that for the submerged wear, normally the let's say the normal liquid level of the oil phase is higher than the weight of the height of the, sorry, not weight, height of the wear. That's why.
it's like
Uh,
fully submerged into the like.
Perfectly. Yep, yep. Because we are normally we are using here normal liquid level. We have the normal liquid level here, and just the normal liquid level is higher than the wear. That's why just we have the submerged wear. Yep. Thanks, Barry. Thank you so much. Okay. The next point about that's about the general separator design considerations. Okay. There are some characteristics just which have great impact on the design and operation of the separator, actually on the separator performance. The first one is the gas and liquid flow rates, because depending on the gas and liquid flow rates, we are defining the orientation of our separator, also the length, also the height, let's say the dimensions of the separator, and the other case also importance of using internal baffles, or uh, let's say all details can we can define. Gas and liquid flow rates can affect to all the, let's say, the parameters, design parameters of the separator. The next one is the operating and the design pressure and the temperatures. Actually, that's mainly point for the mechanical engineers, but that's also our, let's say, the point of interest, because as a process engineer we are also obliged to define and uh, to define and, let's say, so to consider the design temperature and the pressures and also the operating ones, because at least just to fulfill to fill the data sheet in order to supply the vendor with our process parameters. The third one is the surging and the slugging tendencies of the feed streams, because that's the another case just which can affect heavily the separator performance. Actually, it can worsen our, let's say, as a um, separation process. That's why we need to consider also the absence of or presence of these scenarios. And the fourth one is the physical properties of the fluids. We know that the viscosity, density, and just also the other parameter, for example, vapor pressure, bubble point, all of them just are affecting mainly the calculation and the separation processes, separation performance also. The fifth one is the foaming tendencies of the crude oil, because foaming is also another, let's say, a barrier for the separation. That's why we should also consider this case. If let's say that this foaming is severe, we should consider the foam breakers in order to recover the separation performances. I think the last one is the corrosive tendencies of the liquids or gas, because for example, corrosive tendencies, let's say the corrosiveness of the streams or of the process streams define the material, mainly the material of the separators during the design phase, during the feed phase, also the not during conceptual design, mainly during the feed phase. It's very important to consider the material of the separators, so not only separators, all equipment, all pieces of equipment. Okay, let's come now just the criticalities inside separators. We can define them. The first one is the liquid carryover in gas phase. What's liquid carryover? Liquid carryover, it means that the gas phase, the separated gas phase, takes some molecules, liquid molecules from the top of the liquid, let's say, so from the top of liquid level, and just uh, let's say the liquid phase are left is losing some already separated liquid particles in the gas phase, and actually it affects also our separation performances, also the let's say the let's say the product specifications, because in this case we cannot it's unexpected. Actually, liquid carryover always there's always, but if it's unexpected, or just the amount of liquid carryover is, let's say, just let's say just, is unexpectedly higher. In that case, we can also lose the product specifications. What are the reasons for the liquid carryover? The first one is the excess gas velocity. Actually, in case of the elevated gas velocities, we can experience the liquid carryover in gas phase. The second one is the unexpected high liquid level. It means that we are just in the first one we are giving the kinetic energy, not the kinetic energy. Let's say that we are giving the energy to the gas phase because it has the higher velocity. That's why it has more energy, and it can take the liquid molecules, liquid liquid, let's say just liquid particles. In the second case, unexpected high liquid level, we are giving the possibility, not the energy, the possibility to the gas phase to take the liquid droplet, again, liquid particles. Okay, what are the consequences of the liquid carryover? Imagine that the pressure, let's say downstream of the separator, we are using the compressor, and for example, we are controlling the pressure of the separator with this compressor. In this case, because we know that the presence of the liquid particles can damage the compressors, that's why we can have the compressor damage. And in case of the elevated, let's say the liquid carryover, we should have the not we should have we could have the foaming scenarios. Okay, the second criticality is the gas entrainment in the liquid phase. That's the vice versa. Let's say instead gas liquid particles escaping gas phase. Now the gas particles, uh, let's say the gas particles leaves the separator in the liquid phase. What can be the causes for this one? Actually, this can, let's say, can occur because of the low liquid retention time. Low liquid retention time. And the second one, actually, the unexpected low liquid level. And the consequences, and we know that for the um, uh, at the liquid downstream of the separator, mainly we are using the pumps, not always, but sometimes. In case of utilization of these pumps, we can have the pump cavitation, because we know that for example, pump design, we are considering always MPCH, that's positive suction head. Why? Because in order to let's just check the presence of liquid particles at the suction nozzle of the pump, okay, because of the condensation. But here, if we have the gas entrainment, not liquid condensation, sorry, liquid vaporization. Sorry, liquid vaporization. Just we are checking we are checking the presence of the gas phase at the suction nozzle of the pump. Sorry, maybe I just made a mistake. We are just checking the gas molecules at suction nozzle of the pump. But here we don't need to consider the MPCH. Why? Actually, for pump design, we are always just considering the MPCH. But in this case, because we are sure that we have the gas phase, because we have the gas entrainment, that's why just we have the gas particles, and it can, let's say, it gives rise to pump cavitation because of the let's say just, because the gas molecules, we know that they are hazardous for pumps, let's say, so for liquid rotating equipment. And the second one is the liquid accumulation. It can cause the liquid accumulation in the separator. And the third one is the actually we have the liquid carryover in gas phase, gas entrainment in liquid phase. The third one is the light liquid entrainment in heavy liquid phase, and the vice versa. Actually, we have also the heavy liquid escaping in light liquid, but the important one is the light liquid because the light liquid is much more precious. Let's say the phase for our inside the separator because mainly the light liquid, for example, in case of oil plants, it's the light phase is defined as oil is defined as light phase. That's why we don't want to use we don't want to lose our product because our in this case we are losing the money. Okay, what are the causes or just what are the parameters affect this entrainment? They are the viscosities, densities, and the drop diameters of the liquids. Okay, and the bed sizing. In case of the bed sizing,
Can
actually
I
it can be defined as a sorry.
can I ask one
Sure.
question
Sure.
regarding liquid carryover? So we have you have said that consequences can be one of them foaming. Could you please explain what do you mean by foaming and how it will happen?
Okay. Now let's just let me take the one picture of separator. Okay, let's just taking this as a just example. Let's just because we have the gas entrainment here. Sorry, we have the liquid carryover here. Let's say just that's our gas. What was your name? Sorry,
I am Talia.
Taleb. Just please, just in case of any doubts, just stop me and just ask your question. Let's say just that's our gas phase, right? It enters and it takes some liquid particles from here, but from let's say after taking the liquid particles, we don't have the let's say a smooth stream for the both let's say for the mixture of the liquid phase and the gas phase. Since our liquid particles are a little bit heavier, right? That's why just mainly we have the some let's say just a fog, like a fog here. We have some fluctuation here because let's say the gas phase cannot let's say take out all the carried out liquid particles, let's say abruptly from the separator. That's why some of them are just collecting here, are collected here for some period of time. Let's say just 2 seconds, 3 seconds. But because in case of the continuous phase, we have the forming, continuous forming here. Let's say these gas phases take some gas particulates here, liquid particulates here, and just leaves the separator. But all the liquid particles in the gas phase carried out in the gas phase cannot escape the separator. Some of them are collected here. Why? Because we have still we are having this stream, let's say the gas stream here, and then because of the drag forces, because of the potential of the let's say just these gas phases, these let's say the liquid particles are suspended here, like kind of suspended here, and they are making the forms in these let's say just in this section of the separator. I don't know it was clear for you, Talia, or not.
Yes, it's clear, but how will you get rid of these forms in the separator then?
If we have the because we can use some of the form first one just avoiding the liquid carryover. For example, if we have the liquid, we are saying that in case of the why we have the liquid carryover, we have the for example high gas phase, sorry, high gas velocity or just elevate high liquid levels. We can, for example, decrease our liquid levels, or just we can decrease the gas velocity.
Uh-huh.
Or
Okay,
if we
it's
don't have
clear.
any chance, if we sorry, Italy, just if we don't have any chance, what we should do? Let's say just the vendor say that's okay. Just if you change the level settings, or just if you decrease the gas phase velocity, okay, I don't guarantee you that the separator will work just a normal. What we can do in this case, we are using the foam breakers. Mainly just we are injecting before the separator, before the feed entering the separator, we are injecting some some foam breakers in order to break these foams. Actually, they
Uh-huh.
are just kind of emulsion breakers, or just we are using some chemicals for special, let's say, special for as a foam breaker. That was clear for you.
Yes, it's clear. Thank you very much.
But yes, that was the last. Okay, I think we were here. Yeah, we have concluded light liquid entrainment. Yeah. Okay, just the bed sizing. We can see we can define that the bed sizing can be the bottleneck for the whole facility because, for example, if our separator has not been designed properly, it means that there may be all the criticalities we will have regarding this. Let's say all the criticalities we have regarding the facility, all the plant, just will be those of this separator. That's why we should eliminate the bed sizing properly. Always we must design our separate, not only separators, but sorry, we are since we are now talking about the separators. I am just referring to the separators. We must perfectly design our separators. Firstly, okay, just if we have the, let's say, the bed sizing, what should be the consequence of this bed sizing? The first one is the sorry, if we have, for example, the suction scrubber before the compressor, and if we don't if we have not, let's say, just designed our separator, our suction scrubber normally or just perfectly, in that case we can have some uh, uh, let's say the liquid droplets at this compressor section, and it can be very problematic for us just because we don't need the liquid phase in compressor, liquid droplets in compressor, because as much as, let's say, we are just always getting rid of these liquid droplets in order to avoid the compressor damage. Okay, the second one is again the glycol dehydrator. Sorry, but for example, because we know that for the normally for the glycol dehydrator we are using the flash drum, or yes, we are using the inlet scrubber before the glycol dehydrator. That's why if our inlet scrubber again are not designed properly, we can have the foaming in the glycol dehydrator, inside the glycol dehydrator column, inside, let's say, in absorption column. Also, the if, for example, we have not considered the entrainment or the liquid carryover or just the flooding of the flooding regime of the separators, we can have the flooding inside the separator, and for sure we would have the off-spec products. Off-spec products means that meaning that the products just which do not match with the, let's say, the predefined product specifications. And the last one, as we have already said, it can cause the pump cavitation, the bad sizing, because, for example, the low hold up capacity, not only the gas entrainment. Okay, we have already just covered the gas entrainment. We have already just considered that the gas entrainment can be very problematic for the pumps in case of cavitation. But another case is the hold up, because if we don't consider the MPC, for example, during the calculation phase, if we have not sized our separators uh, perfectly, for example, we should have the in some cases we cannot match the MPCH requirements, because we know that for the pumps we have the two types of MPCH available, and MPCH required. If we don't match, if our MPCH available is not higher than the MPCH required, in this case, for sure we would have the pump cavitation. That's why that's again also the another problematic point for our plant. Okay, now just let's consider the separator P&ID. I want to just give you some brief information about the P&ID. Okay, that's our separators, and that's our actually surface separator, because we have here where we have the vortex breakers. Vortex breaker actually are used in order to, as we have already explained in the previous session, are used to prevent the vortices, let's say, just inside the separator. Okay, here these are just the let's say the block valves, which we are in case of the maintenance or in case of the some other let's say it's the case we can use them. They are normally opened, and here we have the level control valve. That's that level control valve for controlling the water level, not the water level actually, the interface actually, this level transmitter, and we have here level controller, and here we are just taking this sensor takes the interface level from inside the separator, and just here we have the predefined set point, and comparing this process parameter with the predefined set point, and it actually the level controller calculate or just determines the opening percentage of this level valve in order in a way to control the interface level or just the water level inside the separator. We have also the same configuration for the oil outlet. Let's say just here in again just we are using the level transmitter, level controller, and just we have here the level valves. They are just the morphology. Let's say is the same. And here, actually, that's our inlet, zero-phase inlet. Okay, that's our pressure transmitter, and that's our let's say the pressure valve, pressure controller. Actually, we can put also here PCV, non PSV, non pressure safety valve, PCV, pressure control valve. In order to that's actually the self-regulated valves. For example, we see that here we are using the sensor here in order to measure the pressure inside the separator. Then we have the pressure controllers, and these pressure controllers determine the opening percentage of the pressure valve. Actually, that's the pressure. But if we use here the pressure control valve, that's a self-regulated valve, and the mechanical the set point has been defined in this valve, and if we don't use the pressure transmitter, also the pressure controllers for in order to control the valve, the opening percentage of the valve, depending on the downstream pressure of the valve, that valve defines this opening percentage itself. That's why that's called self-regulated valve. And actually, that's our vapor outlet. And we have C also for some level outlets. We are using some black ones. It's just we know that these are just the globe valves. Also, this one is the globe valve. That's the symbol of globe valve. Also, this one. If we have this, let's say, the cap on this level, it means that it's the automatically regulated valves or it's automatic valves. These are just a manual valves. The black means that they are normally closed because in case of the maintenance or in case of the some emergent cases, we can open them manually. We can open these manual valves in order to bypass the liquid level. Let's say non the bypass the liquid. Uh, bypass the liquid. Okay, here we are also some let's say the gate valves here. Okay, these are just the reducer. But the interesting point is this one. Okay, what is this one? Actually, that's used for the draining of the line, draining of the separator. We are using the this kind of configuration in order to drain the liquid from the separator. The last interesting point about this let's say the section is the PSVs, pressure safety valves. That's the symbol of the pressure safety valves. Normally, the gas, if the pressure just normally the opening let's say the pressure of the PSV is equal to the design pressure of the separators. Let's say if we have defined it, for example, 25 bar G, the design pressure for the separators. Okay, we set pressure of our PSV is just 25 bar G, and in case the 25 bar G is reached inside the separator, this valve mechanically, let's say just this valve is not a manual valve. That's the mechanical valve. Let's say just, we have the spring mechanism of the spring. In case of the let's say in case of overpressure, this valve let's say opens automatically by means of the spring, because we have some predefined spring force here. If the force exerted by the gas on the spring is equal to the spring force, just if this one let's say is higher than the spring force, the valve, let's say, is opened, and the gas inside the separator is released to the not atmosphere actually, because to the flare. That's the emergent case, but that's not a shutdown. That's not a trip. That's just in order to protect our equipment, we are using this manner. I think that's all about the separator P&ID. The second one is a general arrangement of the separator. I think it's not visible for you. Let me just zoom it out a little bit. Okay, I want to just talk about not all points, or just I want to give you just some brief information how to read the general arrangement or general drawing of the separators. Actually, we see here the nomenclature for the nozzles. We see for example, M1, for example, M1, N16, for example, N10, or just others. Normally, N resembling the nozzles, but M resembling the manholes. That's the manhole. And we have the two manhole. But for example, as a let's say just as a young engineer, let's say as a new graduate, we can also define these. Let's say as the, if you don't have any information about the let's say some nozzles or identification of the nozzles, normally we have this a table of nomenclature here, and here all these nozzles, all these particles are just defined. For example, M1 and M2, and here that's the manhole. Okay. Actually, these are just the type of the welding types. How, and that's the schedule of the, for example, schedule 40, and for example, that's the number of okay, how many manholes do we have here? Just two, and that's a 24-inch. That's a diameter, but a normal. Not a normal, sorry, nominal diameter of the manholes, and that's the rating. And the rating, depending, is the rating actually depends on the design pressure and the design temperature, and each, for example, this rating also determines the thickness of the materials. Also, we have other let's say the types of nozzles. For example, sample box connection. We know that in order to always check the performance of the separation, we have there's some sample points. Okay, and just we can say that here M1, that's the inlet nozzle, and actually that says N2 is the gas outlet. We can also see here N2, eh, eh, yep, N2 is just a vapor outlet. For example, in now just let's look for the okay, that's the N3. That's the light liquid outlet. Let's say it's a oil outlet, and that's the heavy liquid outlet, and just the water outlet. Okay, uh, and all I think that's all about general arrangement of the separator, surface separator. Actually, one interesting point, because during the design phase of the separators, actually for three-phase separators, we will have these, let's say, the parameters. This parameter is just the inlet calming zone. Actually, for example, in this case, 2,550 millimeters. But this point, this, let's say, is the part, or just this section is called effective length. Effective length, for example, in this case, it's the 10,900 millimeter. And actually, this point, actually, that's our wear. If, for example, the scheme is not, let's say, is visible, or just is not so clear, what we can do, we can define the position of the wear by looking at the lens. Because for the three-phase separator, we have this mainly three sections: inlet calming zone, equivalent length, and this the wear section. Okay. And I think we can start the sizing of the horizontal separator. We know that that's our let's say liquid particles. We have the two velocity compartments for these particles. One of them is the horizontal, one of them is the vertical, and that's the depths for the transportation. Let's say for travel of not transportation, for travel of liquid droplet. Okay, G, and that's the equivalent length here. That's our demister. Actually, we are talking about a two-phase separator. Normally, always a slenderness ratio must be satisfied because, for example, as a process engineer, we cannot say that okay, we are just designing the, for example, distillation column or this, for example, in case of the distillation column, because that's the vertical one. Okay, just a half meter diameter and just a 120 meter, for example, the height. As a process engineer, for example, this kind of distillation column can match the product specifications perfectly. But another point, we should also consider the, let's say, the workload of the civil engineers, of the mechanical engineers, because that's the, let's say, that type of let's say equipment is not practical. Let's say is not just possible to mount it, of let's say mount it vertically inside the plant because considering the stabilization, vibration, all these facts, they are we can mount it, but it wouldn't be this stable. Let's say just that's why we need to consider always the slenderness ratio, and the slenderness ratio depending on the operating pressure. We have the there's a different range, different number for slenderness ratio. Actually, slenderness ratio, that's the ratio between the length and the diameter of the separators. For example, for the first range, just in which the operating pressure is between 0 bar G and the 20 bar, 0 bar 20. Actually, 0 bar I have never seen, but let's say just till 20 bar, we should have the three slender ratio equal to 3. In range of in range of 20 and 35, we should have the 4. As we for the elevated pressure, we should have the 5. Slenderness ratio equal to 5. Actually, now let's look at the steps of the horizontal separator design procedure. Firstly, we should define the vapor volumetric flow rate, and by let's say recalling, which is referring to the basic formulas of the fluid dynamics, we can say that from the volumetric mass flow rate, we can define the vapor volumetric flow rate. We should do also the same calculation for the liquid volumetric flow rate. And the second one, the third one is the defining the critical or just the maximum allowable gas velocity. That's the important point. For this, we are using the Souders-Brown equation. Actually, the equation in these ways, let's say depending on the K factor and the difference of the densities and the let's say liquid density minus vapor density divided by the liquid density, sorry, vapor density and the square root of it multiplied by the key values. Actually, now just let's look at let's look at how this formula just have been derived. Okay, let's imagine that that's our liquid droplets, and let's make the force balance on this. Let's say the particles. We have here the inertial force, and here we have the gravitational force exerted on the liquid particle. Here we have two kinds of force: viscous drag force and the buoyant force. Because we imagine that these particles is moving in this way, it's moving, the direction is downward, and that's why the drag force. We know that normally that's the, let's say, directed opposite to the movement direction of the any objects. The movement direction is downward. That's why the drag force is upward. Buoyancy force, we know that always try to, let's say, take out the particles in the continuous phase. That's our gravitational force. Let's define the let's just recall the formulas of this gravitation force. Gravitational force can be defined in these ways: just 1 divided by 6 p, this d cubic of d is the diameter of the particles, rho, and the g. And the let's just inertial forces we can actually, in this case, because we are making the balance
Taleh Bey,
vertically, that's what. Yep, yep.
I am so sorry. Could you please make order your microphone because your voice is interrupting.
Ah, sorry. Now
Mhm.
just could you hear could you hear me?
Yes, yes, it's clear. It's
Sorry, just what was the last point? Just was unclear. Maybe.
no, no. Actually, it was clear, but it was interrupting. That's why we cannot hear
Ah,
well.
perfectly, perfect.
Mhm.
But till here, just till now, you heard all details. Yep, till now.
Yes,
Just
yes.
about okay, perfect. Thanks for informing me. And just I was talking about the force balance. Okay, just for the force balance, we are just here the gravitational force and the viscous force and the buoyant force or buoyancy force, and actually the inertial forces. Now, just recalling the gravitational force, that's the actually 1 divided by 6 times p times cubic of particle diameter and particle density and the g. Actually, if because since we are making the force balance, let's say so vertically, that's why we can ignore for now the inertial forces. The buoyancy forces, actually, that's we know that the buoyancy for formula is just rho v, no, rho of the continuous phase, because here the continuous phase is the vapor phase, rho v um, times volume of the particle and the g, gravitational acceleration. Actually, here the rho is just the density of the liquid, but here rho v, that's the density of the continuous phase. Since in our case the continuous phase is the vapor phase, that's why that's the density of the vapor. And the drag force. Actually, drag force is always defined in this way: 1 divided by 2 multiplied by the drag force coefficient times A. A is the contact area, actually this area, because from this point till this point, in the movement of this direction, let's say that this part of the particle are contacting with the continuous phase, and here v is the velocity of our particles. Uh, I have already just mentioned here let's say all parameters. Actually, A is the not a contacted here, actually projected section. Let's say, but that's same contact surface. If we make the balance between them, okay, just making the force balance, just we can have the Newton's equation, which we have in this way. Let's say the critical velocity is equal to 1.15 square root of gravitational acceleration times d. Pay attention, please. D here is the particle diameter times difference between the liquid density and the vapor density divided by the vapor density and the c. That's actually the drag force coefficient. Uh, we actually we must define the drag coefficient, but how? Actually, that's the drag coefficient is the function of the shape of the droplet. But for the simplifications, always we are considering the spherical cases. That's also the let's say a function of the Reynolds number, and we know that that's the Reynolds number of our let's say the formula of the Reynolds number. Okay, and here just a 1000. It's just for that's the matter of the units. That's why just we, but always we know that the Reynolds formula is just a rho density times v times diameter multiplied by the kinematic velocity, kinematic viscosity. Sorry, kinematic viscosity. And if, always we should consider the units of the part units of the let's say the components. And how we can we define the drag forces? Actually, drag force is equal to, depending on the CD and the Reynolds square, we can by utilizing this graph we can define the C, let's say the drag coefficient. And how can we define CD let's say the Reynolds number and the CD? Actually, we can, by the empirical formula, the scientists, let's say, made this formula for us. We can, by using this formula here, the let's say the unknown parameters is the vapor density that we can find, the diameter, particle diameter, rho L minus rho V, we know, and the viscosity. We see that that's very simple, and by using this formula, we can define the C, and then we can put in the formula. We can put in the place, let's just say in the form. Let's say it's the let's imagine the liquid vapor two-phase separators, and we say that okay, that's our formula, our Newton's equation for the critical velocity. The important point, please, just to pay attention also to this one. Also, when I was in the bachelor degree, let's say, is that we have at least is that not I don't say just I have not been informed by this, but let's just I have not realized this fact. For the separators, always we must consider the particle diameter. Particle diameter, just till which level of the diameter of particle diameters we need to separate, because we cannot separate all the liquid particles from the separate. Yeah, we can separate. In that case, we should, let's say, just we should have the 20 meters for the length and just 5 meters for the diameter of the separator in this case. But at least just in order to match the product specifications, we should make some threshold for the liquid particle diameters. Actually, I will show you later some standard diameters for different applications. Actually, the minimum let's imagine that the minimum separable droplet size is just a 180 micromillimeter, and just let's assume that the drag force is one. It's just for the simplification I'm making here. In that case, I have the formula in this way. Critical velocity is equal to 0.048 multiplied by the square root of the density, let's say the difference of the density, and divided by the vapor density. Actually, now we should define the key factor. The key factor in order to estimate the gas velocity. Actually, that depending on the configuration of the separator and the other factors, we must define it. Actually, the ultimate, let's say, the gas velocity is equal to this. Let's say the formula K prime times U critical. Or critical calculate from this one and the K prime. And then let's now just let's brainstorm about how can we about that. How can we, let's say, define these key values. Okay, here for before passing to the key values, I want to just define to let's say give some brief information about the particle diameters, which I recall here. As I have said, just different applications have different particle diameters, particle droplet size. Let's say as the define it for the separation. For example, for the normal, let's say as the in case of the, for example, oil separators, we are using these sizes. Let's just range from 150 till 180. But actually, I have designed just a one-time flare knockout round, but just a one-time, let's say, the surface separator and one-time flare drums. Actually, designing, I mean, just that was the green field, but for the rating procedures, I have done a lot. But for the designing from the zero, let's say, for the feed phase, I have designed the flare knockout drum. In that case, I remember that I have used 300 millimeter, 300 micromillimeter, sorry, for the flare knockout drum as a particle diameter in order to guarantee the separation performances for the for knockout drum. Actually, by referring to these sections, to these values, we can define, uh, we can choose the base for our calculation. But another case, just I want to inform you that all these numbers depend on the company standards. Actually, for the let's say the for the projects in the university or at the university or just for some let's say some other applications, you can freely you can just you can use these values just and these values will match your let's say, specifications perfectly. But for example, for the future in the real projects, let's always refer to the appropriate let's say company standards, because I don't remember which standards are they, but I think that was the project just which I worked in Turkey, not in Turkey, but for Turkey. That was the polypropylene plant. I remember there is one company which is called Renaissance, and I think that's a standard of this company, as I remember. But I don't just remember very well. Okay. Actually, these are not the confidential values. That's why I'm sharing with you. And now just returning to the key factor. Actually, it depending on the different services and the different companies, the key factor. Let's focus on the key factor. Just in order to define the gas velocity, we must define the key factor. Actually, in order to calculate this formula, we have for this one we have the two method. Let's say the first method is the method A. Here we are using the let's say the table for defining the key values. Here, depending on the let's say the length or height, or let's say for example, in case of the vertical separators, actually it's height. In case of the horizontal separator, it's the length. Depending on the length or height of the separator, we are just choosing one range. But you see that at the very first stage, let's say the very early stage of the designing procedure, since we don't know the length of the separator, we can assume the let's say separator length, and just we can choose the, for example, key factor range from these tables. Another methodology for this one is the as recommended in the Campbell. We know that that's the oil and gas, let's say, it's the reference book which is used in oil and gas industry very well. Firstly, we are defining the effective length, and here the effective length is equal to the normal length minus diameter. And here we are defining these values. That's the KSH is equal to KSV times let's say effective length divided by the diameter, and HG divided by the diameter. You remember HG? What's the HG, right? HG is the height for the travel of the liquid phase. Let's say that's the height between the top of the separator, for example, in case of this horizontal separator, at the top of separator and the liquid level. That shows the height between the liquid level and the top of the separator. That says the wall of the separator, which is void for the gas phase. Actually, in order to define these ones, we must let's say assume these values. We must assume these values LAD and the HGD. Sorry, what I wrote in here. These values assumes no. Because just before the sorry, just one point. Ah, Actually, these values are because the separators are equipped with the standard mesh extractors if we are using this table. But sorry for interruption. Please, oops, ignore please this sentence. Sorry. Perfect. Okay. But how can we define, let's say, just our key values? Um, let's say just from here we can choose our operating pressure. And I don't know, you see the table or not? Let's put in this way. Okay, let's make it in this way. For example, by choosing the appropriate droplet size, for example, 500 micron or 300 micron or 150 micron or just a 100 micron, and by defining the operating pressure, we can define the KS values, and from the KS values, we can calculate the KSH values, and then we can put this value in the formula in order to define the critical gas velocity or maximum gas velocity. And actually, the designing of the horizontal separator is just a trial error procedure, because we know that firstly we are assuming these values, these ratios. We are assuming these ratios, and after assuming we are calculating KS values, then we are calculating the maximum gas velocity. Then by using this equation, actually this one, LA, we are defining in this way. LA is equal to 4 times T. T is the residence time, which we have shown before. That's the QL. QL is the actual liquid flow rate. That's the P. D square. D is the diameter of the separator. And the FL. We know that here we don't know the diameter. That's why we need to define the diameter. That's why the diameter, we have this formula. 4 times QV. QV just we know P and the critical gas velocity. And just we have already defined these values. And after defining and after putting these values here, after calculating the let's say just the length, we are just again checking the slenderness ratio of the separator. If it's not in the range, we can change the parameters. For example, simply we can change the HG values in order to match, in order to, let's say, some match process parameters, process requirements. And then the next step is to define the hold up volume and the surge volume. Actually, the hold up volume is between the volume between the normal liquid level and the low liquid level, and the surge volume instead is the volume between the normal liquid level and the high liquid level. And in order to define them, VH is equal to TH times QL, and the VS is equal to TS times QL. But okay, just we are let's just we have information about these parameters QL, but how can we define the TH and the TS? Actually, we have the predefined, let's say, as a table in order to define them. Actually, depending on the different applications, we have the different numbers for the hold up times and for the surge values. Actually, by knowing this, let's say, the table, we can use another methodology for determination of the separator diameter. Actually, that's in this way. Let's say without passing the from uh, actually here, because we should calculate the QV, UV, but here you see that we are only putting here 4, let's say 4 times VH, VSP 0.6 at the slenderness ratio. That's much more simplified form of separator, let's say the determination of the separator diameter. And for the FL values, just the one value, sorry for okay, just for inconvenience. You see just here FL. What's the FL? FL is the fraction of the cross-section area. Cross-section area occupied by the liquid. How can we define this? Actually, we can calculate, we can make also the hand calculation for the two, let's say the two to one ellipsoidal vessel. That's actually normally the common shape for the separators. We can define it by this formula. That's our diameter. That's the length, let's say, liquid height. And by just defining this formula, we can define the FL. And uh, okay, now just I want to make one just activity for not activity. Let's make one brainstorm with you. Just let's assume we have the slugging regime, and your friend. I think I do apologize if I made mistake. Just I think Talia made a question about this, not the foaming, not the slugging, but about the foaming. But that's another interesting topic, just a slugging regime in the separator. Let's imagine we have the slugging regime inside the separator, and let's say, so what do you how you think how can we avoid this regime? Firstly, just please let me know, just any one of you does not information about slugging. If just, you're not familiar, I can just give brief information about the slugging. Slugging, actually, in case of the slugging, for the liquid phase, we have the fluctuations in the liquid levels. That's why, for example, we have the risk of gas entrainment, or all other, let's say, the criticalities. That's what all we have. That's why we should let's say we should avoid this slugging regime. But how? And let's say the how can we how not not always avoid the slugging regime. Let's say that we have the, let's say, the slugging regime. How can we optimize the separator performance? Actually, the optimization methodologies are a little bit peculiar, are a little bit, let's say, specific. Let's say specific, which I have seen them based on my experience. I have seen them, let's say, in some projects, um, which I was involved to. But I want to just make you the questions. Can you just please do the brainstorm? How can we, let's say, optimize the separator performance in case of slugging? Any one of you?
Talebe.
Yep.
So we said that slugging is kind of creates turbulence inside
Yep.
of the liquid, right?
Perfectly. Yep.
We kind of have these calm baffles. And we kind
Perfect.
of mentioned about it that it can create turbulences. So maybe we can.
Perfect. Actually, the first solution is like that. Yep. Perfectly. Your name is Perry, yeah? As I seen Perry.
Yes, yes,
Yeah,
it's me. It's me.
perfect, very perfectly. Just really just bravo. I want to say just really we can use the baffles here, inside internal baffles for this. Okay, Pari, please don't mute your microphone. Okay, just
Okay.
let me just make another, let's say, a case study for you. Let's imagine that let's imagine that okay, the first let's say the mitigation of the slugging regime, or just is perfectly just you have said. Let's imagine that we have the because we have the fluctuation on the liquid level, and we have the turbulence. That's why our control valves also cannot, let's say, the liquid outlet from the separators are not stable. Am I right? Because we are
Hey,
just changing. Yeah.
yes.
And in this case, for example, we can give the damage to the downstream equipment. For example, we have the heat exchanger downstream the separators. For example, we are using their utility heat exchanger, and always we are just in every moment, just we are changing the opening percentage of the utility side of the heat exchanger. We are closing, opening, closing, opening. And just how can we mitigate this, let's say, scenario, this case? What do you think about that? We have the fluctuation,
Yeah, yes, we have fluctuations. So,
turbulence.
you mean how we can control the valves to kind
Not
of?
actually. I just said because our aim, let's say, just our aim is to have this stable flow rate at the outlet of the separator before entering to the heat exchanger. Since let's say, in order to decrease the damage, the possible damage to the downstream equipment. Let me just make the question, let's just much clear for you. Just also other friends, just if any one of you just makes let's say, wants to make answer, please feel free. Let's imagine in this way. We have the fluctuation turbulence in the liquid phase, and since we have the sensor here, let's say the process parameters, operating parameter changing let's say, in every moment. And then we have the set point, right? That's why just the always just the error, just which is accepted by the level controller changes. That's why the opening percentage of the level control valve changes. That's why also the flow rate, which leaves the separator changes. And process engineers or just the maintenance or let's say the inspection, let's say the personal define it that this kind of change, this kind of fluctuation of the flow rate, unstable flow rate, can give the damage to the, for example, the downstream equipment. For example, imagine that in our case that's the heat exchanger, can give the damage to the heat exchanger. Now our they just asked our let's say asked us, let's say so we are the process engineers, and they asked us to have at least, because let's imagine that we cannot avoid the slugging regime, they asked us to mitigate or just to mitigate the instability in the, let's say, the flow rate, discharge flow rate, or just asked us to have the stable flow rate in the uh, separator, separator liquid output. My question is that how can we have uh, this, let's say, just a stable regime, stable flow rate in case of, even in case of slugging regime? Imagine that we have the fluctuations, again fluctuations, turbulence in the liquid level, but if we have the, let's say, this much more stable liquid outlet. How?
Uh, I don't know, but maybe kind of increasing the height of the liquid. Um, so there is more liquid height,
uh,
say.
More liquid height, but again just we are just since we have the slugging regime, again we have the turbulences, again just we will have the fluctuations in the let's say in the sensor which measure the liquid level. Actually, that's a little bit peculiar. If you agree, I can give you the. That's really interesting point. That's why I wanted to share with you. Just if can I just go through? There are no answers. Okay, that's again just one point. It's the gap removed set point. By actually, that's not a physical, so let's say it's a sensor, but imagine that we are putting the delay to the controller to the, and that's called just a gap remote set point, and we are making it by the DGS is distributed control system. By inserting this one, the measured variable, let's say it's a if, and if we are defining the maximum level, level alarm and the low level alarm for the separator, for the separator. If our liquid level is higher than or equal to the high liquid level, the sensor always show the maximum, let's say it's the high level. Let's say just let's imagine that we put the level settings high level 800 millimeter and the low level 300 millimeter. Okay, sensor just measuring 850 millimeter. In that case, the gap remote set point makes this 8.50 millimeter equal to the 8 not 8.50, sorry, 850 millimeter, equal to the 800 millimeter. Just let's just consider this value as a equal to the high level, high alarm level. But in case of the low, if let's say just the sensor measures the 300 millimeter or lower than, for example, the 250 millimeter, sensor considers the liquid level equal to 300 millimeter. And if the sensor measures a value between the 300 millimeters and the 800 millimeters, in that case, it says the remote set point is ignored, and we are the controller considers the actual measured variable. And by inserting remote set point, and the operator can define the maximum and the maximum and the low level. And in this case, we can have much more stable liquid flow rate and a much more stable let's say the signals from the sensors. That's why much more stable uh, liquid, let's say, much more stable liquid flow rates from the separator. I hope it's clear for all of you. If someone has, let's say, has any doubt, please let me know. We can.
Yes, can I ask a question?
Sure, sure, sure.
We said that, by the way, I am Talia.
Yep,
We said that the low level alarm is 300 millimeter and
yep,
high
yep.
level alarm is
But
850
that's just
millimeter.
example, yeah. Just example, yeah.
Uh-huh. Yes. And in what case we will say that remote set point is ignored and will take actual measured value?
If the sensor measures the value between these, let's say, for example, it measures it's the level is the 400 millimeter. Okay, we are
Uh-huh.
considering the actual, let's say, the measured variable. For if we measure the variable, not to be, let's say, if the sensor measures the variable between the high level and the low level, and in our case they are just 800 and the 300 millimeter, we are considering the actual, the measured variable. Let's say not,
Okay.
let's say the variable shown on the sensor, shown on the sensor.
And
Yep.
you have written here a set point will be equal to the low set point if the level is less than
Yep.
less than or equal to So for example,
Yep.
let's say if it's 200, we'll
Yep.
take what?
300 millimeter.
Okay, it's clear now. Thank you
Yeah.
very much.
It, welcome, welcome. And the main purpose here is to have the, just please remember this one, is to have the stable flow rate in the separator. And the third one, and the last one, just not the last one, just last one, just which I shared here for the HP separators, uh, is just actually the, as I have just explained over changing the wear type, changing the wear, let's say, the configuration. If we are just operating in the overflow wear regime, and if we have the this slugging regime, we can change the overflow wear regime to the submerged wear regime. In this way, we should have much more stabilized, let's say, the flow rate at the liquid outlet, and in that case, we can consider no, we can operate in a much more stable way. But please, always in these sections or in this part, just always try, not to try, just that's the strongly recommendation, contact with the vendor. Because, okay, just we are using as a process engineers, we are always using the process engineering, let's say the data sheets or just a process engineering spreadsheet to calculate the separators. But the that's mainly, for example, the also the theory I just explained here, that's just a generalized theory. But every vendor has its own, let's say, has its proper model for its, let's say, the manufactured separators. That's why in order to um, calculate, or in order to check the performance of the separators, if we change the, for example, if we change from the overflow wear regime to the submerged wear regime, vendor must be contacted always. Actually, not must be, but it's strongly recommended. It's strong recommendation actually. Now, just let's pass to the vertical separators. Just in case of the vertical separators, we have seen that in the horizontal separators, we cannot define the length and the diameter independently on each other. But that's not valid for the vertical separators. We can actually define them independently. Actually, for the vertical separators, we are again using the same formula. Umax is equal to k times the square root of the rho L minus rho V divided by rho V. And the dV is equal to square root two, 4 times QV divided by P and the UV. UV actually is the maximum velocity. And here, that's our vertical separator. Actually, here, that's our inlet, and that's the inlet diverter in order to decrease the momentum of the inlet feed. That's the liquid coercion section, the liquid, let's say, the outlet. That's the interface, and the gravity is this zone. it's the gas phase zone. We have the settling section. That's the mist extractor, and that one is the pressure control valve. Very simplified form. Okay. Now just here we have defined the diameter of the vertical separators. Now let's look at to the length of the, or not the length, sorry, height of the vertical separators. How can we define them? Actually, we have the predefined methodology for that. Let's say that we have the H1, H2 till H8. Here we have the low alarm, low level, not low alarm, sorry, low level, normal liquid level, high level, high level. Uh, and here it's the TL, here it's a tangent line. It's the vapor outlet, liquid outlet, and that's the feed inlet. Here, actually, we have this table in order to, let's say, to calculate the H1, H2, H3, H4, and till H8, till H8. And for example, we know that the max 15% of the diameter or 400 millimeter for the distance between the mist eliminator and the top side. Actually, this one. For example, for the top side, for the mist eliminator, top side and the mist eliminator. For the height of mist eliminator, for example, 100 millimeter, if it's selected. And also other parameters, we can define all of them. Then we can sum up all of them, and then we can find the height of the vertical separators. My, let's say, the speech about the separators is all about these. Actually, if you have, well, now just I think I have the, I have the time. We can dedicate some minutes for your questions, if any.
Tayyip, actually, I have a question about
Sure.
the DCS, modified DCS. A few minutes ago, I have asked the question, but so let's say again, 300, it's our low level alarm,
Yep. Yep.
and
Yep.
850 high level alarm. So let's say in our case, this
Again,
is
could you please say
200
the numbers? Sorry for interruption. 850 and the 350. You said
and 300. Yes, this numbers are the same,
yes,
and
300 and 800. Okay. Yeah.
and we got 200, let's say 200 millimeter,
Yep.
which is
Yep.
less than the low level alarm,
Perfect.
or
Yep.
900,
Yep.
more than high level alarm.
Yep.
And
Yep.
it's not, I cannot understand why we should take low level alarm value now. So for example, 300,
Yep. Okay. Just
because in the
yeah. Yeah, no, no, no. Please, please. Let's just conclude your sentence. Sorry for interruption.
No, no problem. But I couldn't explain what did I didn't
Just
understood. Yes.
because just
Uh-huh.
Talia, actually, I also put, let's say, let's say, 20 minutes just to um, I just talked with the senior engineer in order to understand this one. I know just it's a little bit it's just a complicated topic. Let me just take here one example. The levels where actually here. Actually, let's imagine that here we have the slug regime here. We have the slug regime here, and we are saying that that's our normal liquid level. Yeah. Yes. And here
Yes.
in the controller we have given the, for example, high level is the 800 millimeter, and the low level is the 300 millimeter. Okay. And as a normal liquid level, we put, for example, 500 millimeter, and that's our set point. The controller, the level controller considers the error, let's say the measured variable minus set point, right? Am I right?
Yes. Yes.
Yeah, minus set point. Okay, just let's imagine that the, for example, since we have the slug regime, we have the 900 millimeter, yeah, 900 millimeter. And in that case, the error is 400 millimeter. 900 millimeters minus 500 millimeter in absence of
Uh-huh.
the gap remote set point. And the controller takes action for the difference of 400 millimeter. That's why closes much more. Let's say, so much more than a normal level control valve, right? But let's imagine that if we have inserted gap remove set point. Now, in case of the 900 millimeter, if reach the 900 millimeter, the sensor still considers the level equal to 800 millimeter. That's why now the error is the 300 millimeter. My voice is clear or not? Uh,
Yes, it's clear.
Now just the error is just a 300 millimeter. 300 millimeter. Now, let's say it takes much more, how to say, just a much more, let's say, stable or much more, let me just define it. How can we define it? Let's say the level control valve now just is closed, not as we had in absence of the gas remove set point. For example, uh, no, let me
There's kind of small
uh,
and small change, like it doesn't affect that much. They're more
if that's
stable.
because during the turbulences, just in every moment, just we are reaching to the, for example, 900 millimeter, then 300, 300 millimeter. Just we are the level actually is just the, how to say, just is just how to say, is changing, let's say, just continuously and rapidly between let's say, yeah, the liquid level, just this measured variable is changing, let's say, rapidly, and really just significantly changing. See, for example, from the 3 millimeter to the 900 millimeter, then 400 millimeter, then, for example, 1000 and 1000 millimeter, like in this way. In order to make the signals much more stable, that's why just we are putting the because let's say just in the slug regime, okay, we have the 900 millimeter. The sensors takes the measures the 900 millimeter. That's why the level control valve takes the action for the 400 millimeter of the level. Let's say the error. Let's say the level control error. Let's say just previously the valve opening percentage was, for example, 60 percentage. Now, because we have the higher the liquid level higher than the normal liquid level, now it closed the level control valve to the, for example, 20 percentage. But after a second, the level decreases to the 300 millimeter, not because of the the contribution of the control system, because of the slugging regime. That's why now, just for example, now we need to open the control valve. We need to open the control valve because now just the valve, the liquid level dropped, let's say, drops to the 300 millimeter. Now we have the error minus 200 millimeter, minus 200 millimeter. That's why now we are opening the valve. That's why always valve also is always opening, closing, and we know that considering the mechanical structure, mechanical parameters, for example, stress, strain, or just a fatigue, or just a fracture of the valves, that's not also the good point for the, let's say, the valves always just changing, let's say, just rapidly and significantly. I don't know, just it was, if it's not clear for you, just to make the question, please. Just don't hesitate.
Actually, it's clearer than the previous explanation,
Yeah.
and I research about it for the next week. And if I have any questions, I will ask you.
Sure, sure, sure. If you want also, just please write me on the mail. Just if
Mhm.
any one of you, just I can also provide you with the, uh, let's say, just with the some.
Material, you mean?
Yeah, it's some, not the material actually, by hand drawing. I can draw it, let's say, so
Uh-huh.
by hand, and then just I can share with you, just because here really I cannot draw in the paint. That's why just, I don't risk. I don't want to get the risk to open of, let's just opening the paint. That's why, because in that case. It would be just a real mess. That's why. Also, I can share with just with you also the with any just our friends who would like. But actually, just what was the point which is unclear for you here now?
It was now it's clear, but most probably after the session, I will have some questions about it
Perfect,
when I think, and I will ask again.
perfect, perfect, perfect.
Mhm.
Okay. Other questions regarding?
May I?
Sure, sure. Why not?
Uh, I wanted to kind of clarify this search volume. I understood the hold up volume, but search, I kind of didn't get it that much. What was the search exactly? The definition of search in separators, like?
Yep. Okay. Actually, the hold up volume is the low is the volume between the normal liquid level and the low liquid level, and the surge volume between the normal liquid level and the high liquid level. Now let's go to this section. The liquid level. Oops. No. Let's copy this here. S- I wouldn't save it. But okay. Perfect. Actually, the hold up volume is the volume between the normal liquid level and the high liquid level. No, sorry, normal liquid level and the low liquid level. The liquid volume between the normal liquid level and the low liquid level. The liquid level from here till here. The surge volume instead. That's the level volume between the normal liquid level. That's the surge volume. We have defined it in these ways.
So, for example, if the search volume is kind of too high, um, it
That,
means like there are more gas at the upper side. So,
no, 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 no. That's a low liquid level. We are always talking about the liquid. Surge volume of the liquid and the hold up volume of the liquid.
why we define those values? Like for what? For
Because
like
okay, just because as we see just here we are always just using, let's say, that these predefined values in order to have the, because let's say just normally we have the high liquid level, right? We have the high liquid level, but the highly in case of the high liquid level, which signal we are receiving? The alarm signal that we are reaching to the emergency case high liquid level, because after the high liquid level we will reach the high liquid level, which will trip all our plant, at least a separator. And the low level the same, just it will shut down, for example, the pumps just the downstream of the separator. And that's why, in order to, for the safety purposes, for, let's say, just we should define that we should give some, let's say, the time to operators or just to personnel on the plant to take action, to take action and not to take, let's say, to take action from the, no, just I made a mistake, sorry, just I forget about that. For the hold up and the search volumes, since in order to have the stable operation, because we should guarantee that we have the let's say, yes, we have the sufficient time between the high level and the normal liquid level. It means that if we consider these values and if the level reach to the high liquid level, it means that really it's just that we have the kind of emergency case. If we put the 1 minute, okay, just because in case of the control of the liquid level or just a control of the process, we cannot say that the liquid level always is, let's say, on the level of the normal liquid level. Always it's changing between the high liquid level and the low liquid level, high liquid level and the low liquid level. And if we consider the delay time of the sensors, if we consider the delay time of the level controllers, if we consider the level controller valve delay time, all these facts, if we consider, we should give this time to the level controllers before showing the alarms. Let's say just if we let's say so put the high liquid level just above the normal liquid level, just for example for example, no, 60 millimeter, let's say so 670 millimeter over the normal liquid level. In this case, just every second we will receive the high liquid alarm, and in that case, just because of the noise, we cannot stand in the plant. Always just red alarms and just alarm. Always just we have the alarms. That's also the case for the low liquid level. In order to have the safe and the stable operation, we are giving these values to the surge for the surge volume and for the hold up volume or the hold up volume in order to guarantee the normal operation, because always our not always our liquid level is equal to the normal liquid level, let's say, is perfectly, because we are always trying to operate yeah, exactly on this point, but then never we can reach it. So for a for a, for a long period we cannot reach it. That's why we should take the margin between the high liquid level and the low liquid level, also the normal liquid level and the low liquid level, in order to guarantee the normal operation. Because if we every moment if we receive the signals, alarm signals, in that case, just always just we will work in the plant with anxiety. Let's say. I don't know, just I think Perry, yeah.
Yeah, yeah, I
You,
got it. I got it.
that's clear
Yes.
for you, really clear for you.
Yeah, yeah, it's
Perfect,
clear. Yes.
perfect.
Thank you.
Okay. Then the next questions.
If there are no questions, we can end up our session, I believe.
Okay. We have meeting chat. No. Yeah, perfect.
Mhm.
Actually, my just I'm appreciated for your patience and just for your time to just to dedicate your time for our sessions, and I hope just it was really useful. And let's
Yes,
just
sure.
I hope just I hope no, no sorry I hope just we will meet in the next sessions. I think it's just already next session will be about absorption. Absorption
Okay.
and absorption
Thank you very
process,
much,
criticality.
Taleh Bey,
Thank you.
for the
Thank you.
great session. And the participants will have also additional session at 6 p.m. Okay. Thank you very much, Taleh Bey. Have a good day.
Welcome. Have a
Thanks a
good.
lot for your time.
Thanks. Thank you so much. Have a good weekend. Have a good day.